I will begin with a word of prayer. So, dear Heavenly Father, we thank you for the weekend just completed. Thank you for the students who prayed with us today. Help us to just understand differentiability in the abstract as best as we can. Lord, we just pray that you be glorified in what we do this day, Lord. In your name I pray. Amen. Okay, so I think I still owe you guys one more example from the limits in topology. And so one of your homework problems, I asked you to show that if you have a set just containing, 1 point basically, it's closed. Now, I think I asked you in the context of a matrix, but you could easily, if you prove it for the matrix, you can prove it for anything. Anyway, so the example I want to do is just this. G, L, N, R, which is, what is this? This is the general linear group of n by n matrices. So it's a set of invertible n by n matrices, all right? So this is A in our n by n such that, oh, Loren, I have it, I changed plans. Could you, you might need to pan it and zoom it, yeah. Such that the determinant of A is not equal to 0. All right. So that's the definition of the general linear group. Of order n, right? With respect to the reals, of course. Now, I want to show you how we can argue that is in fact an open set. This is an open set in the space of n by n matrices, where the notion of open is defined by the Frobenius norm. So I claim GL and R is open in R n by n, where we define the norm of A to be equal to, well, squared, to be the trace of A transpose A, which again is just a sneaky formula for, looking at the Euclidean length of the corresponding n squared vector. You just list out the components. All right, so that's the claim. Let me show you the proof. So basically the proof is using the continuity of the determinant. So determinant's what? Determinant of A, there's a formula for it. It's the sum I1 through In of epsilon I1 through In. This is the completely antisymmetric symbol. And then you do A1, I1, A2, I2, so forth. So this is a completely anti-symmetrized sum over the columns. Okay, that's, yes?
In your notes, I didn't completely understand what the completely anti-symmetric symbol was, what the translation with the epsilon.
Yeah, sure. It's epsilon 1, 2, 3, so forth and so on, all the way down to n is equal to 1, and then you obtain, a minus for any row, for any index swap. So like, for example, epsilon 2, 1, everything else the same, would be equal to minus 1. So if I flip any 2.
Okay, any 2 of the indices of the epsilon.
Right. And then the other thing that's important to notice is that the if you have any repeated index, if you have like 1 and a 1 somewhere in that list of I1 through In, if there's any repeat, 0. This is the definition of the symbol, the antisymmetric symbol. So, well, here in 2 dimensions it's easy. Epsilon 1, 2 is equal to 1. Epsilon 2, 1 is equal to minus 1. And then epsilon 1, 1 equals to epsilon 2, 2 is equal to 0. That's the symbol in 2 dimensions. In 3 dimensions, you've got 1, 2, 3, 2, 3, 1, 3, 1, 2 all be giving you 1. Then 3, 2, 1, 1, 3, 2, 2, the other one. The cyclic give you plus, the anticyclic give you minus. Those are the 6 terms you see in the cross product, which is why you can write the cross product using this antisymmetric symbol. The Levi-Civita symbol. Yeah. Levi-Civita was, one of the early. He did important work in how to calculate in differential geometry, which laid the framework for Einstein to write down general relativity in the early 20th century. Anyway, so that's just a formula. I mean, bottom line is it's just a formula. This epsilon's either plus, minus 1, or 0. And that turns out is all you need to write the determinant, right? Now the formula you were taught the determinant by was maybe an expansion by minors or something, right? You take the submatrices and you go across the top row plus minus. This is just a compact formula for all of that. All right. Now, excuse me. The point then is that this is what? This is a polynomial, an nth order polynomial in the components of A. Right? But you can easily prove that the ijth component of A is a continuous function. In other words, if I go, say, from A and map to aij, that's a continuous function. So what you're looking at is the sum of products of continuous functions. In other words, the determinant is a continuous function. Determinant is a continuous function for where to where. Determinant's a continuous function from the n by n matrices to the reals. So basically what we proved last time, or at least I gave you at a minimum some plausibility arguments to see that if you take the sum of continuous functions, you get another continuous function. If you take the product of continuous functions, you get a continuous function. So determinant's continuous. Now, one of your homework problems is to show, hey, for a continuous function, the inverse image of an open set is open. All right? So what is GLNR in terms of an inverse image? If you look at it, the determinant, the inverse image under the determinant of the following set. Minus infinity to 0, unioned with 0 to infinity. What is that? I mean, that's all possible non-zero real numbers. The inverse image under the determinant of that is exactly what we call GLNR. So this is equal to GLNR. So we have the inverse image of an open set under a continuous map. Therefore, the general linear group of order n is an open set. Now, that's actually, all right, let's take a step back. Like, what does that mean? That means if you give me any invertible matrix, right, I can find an open ball of matrices around that matrix, right? I can choose a ball small enough so that every single other stupid matrix in that open ball in this set of matrices is also invertible. So there are infinitely many other invertible matrices near a given invertible matrix, where near is defined in terms of this so-called Frobenius norm. Which, by the way, in case you're wondering, is not that complicated. Here's the Frobenius norm of 1, 2, 3, 4. It's the square root of 1 squared plus 2 squared plus 3 squared plus 4 squared. It's just, you take the silly matrix and you list it out as a big old vector and calculate the Euclidean length of that. It's nothing too fantabulous or anything. All right? So anyway, I just wanted to show, that was, one of the sort of applications you can make of the last lecture to just a particular problem. Through similar arguments, you can show that here's another set of matrices which you sometimes like to look at, SLNR. What's this? This is A in Rn by n such that what? Yeah, the determinant of A is 1. So in other words, this is the inverse image under the determinant of the set just containing 1. What does it mean for a set to be closed? It means the complement is open. What's the complement of the number 1 in the reals? It's everything but 1, right? So it's like minus infinity to 1, unioned with 1 to infinity. So those are open sets. The union of two open sets is open. In fact, the set just containing 1 is a closed set. So you can similarly argue that the special linear group, SLN, is a closed set of matrices by corresponding argument. But I have given these as homeworks in, like, I think last time I taught this, but I thought for this time I'd just explain it to you guys because it caused much travail for the class when I assigned it. It wasn't meant to be a big deal. It should just be a discussion we have, you know. Okay, I'm trying to give you some exposure to topology. I'm not trying to make you into topologists, right? Okay, so let us move on. Any questions? So maybe you're feeling a little bit overwhelmed right now. I don't know. I know I'm feeling overwhelmed right now because I didn't bring my computer. Or did I? Ah, ha-ha! So some of you have printed out my notes, so you haven't noticed what I'm about to show you. But I felt like I should show it to you. Yeah, indeed. Yeah, the 2015 is done, and it's for the most part the same as 2013. You know, I will include add-ons if I do more. I'm not going to keep fussing with it because I have too many other irons in the fire at the moment to completely fix it. You're like, so you're telling me you're going to spend less time scheming against us? I like the sound of that. Yes, that's true. Come on. So I don't know, how many of you actually clicked on this? Nobody, right?
I didn't know the link. I was looking for it.
Oh, you should stay. Just hang out for a second. So this is so you can understand 30 seconds. Oh, come on. What's ad block? Does ad block work for YouTube?
Yeah, it works for, yeah.
I know I use it.
I use it for, we went with Pandora.
Oh yeah, Pandora is amazing with ad block. That's true. Oh, here you go.
Just found a marble in the oatmeal. Lucky little boy. You know what?
Sorry. I'm spending entirely too much class time on this, but you'll forgive me. I think it's important to watch this clip so you can, you know, understand. Oh, come on. What? Sorry. Hey. I plugged it in. Oh. Watch, now you'll be deafened. No? Nothing? All right. All right, we'll have to be quiet.
Oh, Joel Miller, you just found a marble in the oatmeal. You're a lucky little boy. You know why? You get to drink from the fire hose! Okay, you ready? Open
You guys never seen UHF? It's Weird Al's movie from 1988. Came out the same. Came out the same summer as Batman. It's not that well known. This is Weird Al's movie. That's Kramer. I mean, it's Michael Richards. But yeah. So I think that's like the appropriate video to watch before chapter 1. That's why I put the link there. So my point is, it's like drinking from a fire hose, in case you haven't gotten it yet. But I mean, I think chapter 1's a little bit dense in my notes. Yes. Get the drink from the fire hose. Yes. That movie is hilarious.
Pretty sure we all knew what we were getting.
Ah, yes. Uh-oh, I lost one. All right, so we have limits. We have continuity, right? We have basic topology. Now we can turn our attention to the problem of differentiation. All right, so that's what I want to talk about today. How do you differentiate? How to differentiate in a normed linear space. All right. So I guess the question is, what is a derivative, right? I mean, what is a derivative? What would you guys say? Plead the fifth.
I don't know if my definition is going to be general or not.
Well, I'm not looking for the general. I mean, I'm going to hopefully give you a general definition, relatively general. But, in your previous experience, like if you had to explain to a kindergarten what a derivative is, what would you tell them? It's slope. Okay, I like that.
The function of the slope at any function at any point.
The slope, the function of a slope. So you're thinking of the derivative as a function, very good. But it is true, what I'm about to explain is really more, at the moment, at the start, it's really more like the slope, right? What I'm trying to describe is it's sort of the generalization of that. So let's just go back to, how about a function? Say from the reals to the reals, right? We could go back to that. What did it mean for it to be differentiable? Differentiable at x equals to a, what did that mean? We had f prime of a, right, was the limit as h goes to 0 of f of a plus h minus f of a over h. Remember that thing from the start of Calculus 1 that you guys like to forget? The definition. So that if that limit exists, if that difference quotient exists, then we say that f is differentiable at a, and the derivative of f is the value f prime of a, right? That specific number. Now, what I will say is, like, basically what this is it's it's the best approximation to the change in the function at a, right? And that's a different way of saying it's a slope, right? It's the best approximation to the change in the function. Now, let's see here. So we can rewrite this as follows. You can say, okay, well, this is really the same as saying the limit as h goes to 0. And I can say, okay, so I've got f of a plus h minus f of a divided by h, right? And if I subtract f of a to the other side, I can do this, right? Now, I don't want to do too much writing, so that was my first step. You guys got me logically? Are you with me? Then, to make a common denominator, what do I do? All right, divide by h, so I just do minus f prime of a times h. The derivative of a within the limit. Yeah, I put the derivative inside. I mean, this is a constant, right? So I can right, this is the limit of f prime of a is equal to the, I mean, this is equal to, let me do this Manga-style calculation. The limit as h goes to 0 of f prime of a, I mean, that's just an identity. The limit of a constant is a constant. And then I can put it the other side, right? So this actually goes to show you that approximation thing I was just telling you about. So the change in f, right, is f of a plus h minus f of a, right, at a. And as you can see, that is very closely approximated by f prime of a times h. Or if you like, you could define the so-called linearization, right? The linearization of f, centered at a, at h would be equal to f of a plus f prime of a times h. So this is the best affine approximation of f at x equals to a. So we want to come up with a definition of a derivative, right, for a normed linear space. So how should I generalize this? I mean, I think the key message to take away is that the derivative should be somehow tied to the best linear approximation to the change in a function from a normed linear space to a normed linear space, right? And this difference quotient. Well, this isn't the difference quotient anymore. This is called the Frechet quotient. This is what we're going to leap off of, and so that's where we get our definition from. Here's the definition. If V and W are normed linear spaces, all right, with norms, let's say, sub V and sub W respective, right? And let's say that F is a mapping from some perhaps subset of V to W, but it's a mapping from one normed linear space to another, all right? And A is an element of V for which, well, A is an element of V, and let's see here. I'm just going to, this is a sort of temporary notation for the purpose of this definition, but let's say L is a mapping from V to W is linear transformation for which, and then here it is, the limit as h goes to 0 of, parentheses, big old denominator, h downstairs, big F of a plus h minus f of a minus L of h. Say if that is equal to 0, then F is differentiable at let's say, well, at A, with differential, and here's the notation for the differential we'll use, D sub A, F, the differential acting on H is equal to L of H, okay? So I wanted to separate the role of the differential from the notation for the differential. That's why I used L in the definition, and then I gave you the notation for the differential down here. And there you go. A function for which this limit exists, meaning that there is that linear transformation which gives you the best approximation to the change in the function at the point. That means that the function is so-called Frechet differentiable. This is the definition of a Frechet derivative. All right? Now, can anybody tell me why my equation is nonsense? What kind of limit am I taking? That's true, but that's always the 0 over 0 is the fine line we are forced to walk by the theory of differential calculus. It is not a quirk of the theory, it is an inevitability. Right? Those limits are not things that math teachers teach freshman calculus students just to be mean. It's the nature of the beast. I mean, 0 over 0 is the derivative. That's not what I'm getting at.
It's a real limit?
It is a real limit in the sense of real normed linear spaces. That's true. That's our context. I should say real normed linear spaces because I mean, it's a multivariate limit. This is h, right? H. This is a limit in V. So this is that limit we defined in terms of the norm on V last time. It means for every epsilon greater than 0, there exists a delta greater than 0, such that if you take h within delta units in terms of the V norm of 0, this quantity is within epsilon units of 0 with respect to the W norm. Well, the thing is, I'm dividing by h. H is a vector in V. You shouldn't let me do that. I can't divide by a vector. Right? H could be a matrix. I'm taking all the matrices really, really close to 0. Many of which are not invertible.
Would it have to be a normal H then?
Yes. The fix is not that profound. You just put norm h here. Now, some people put norm of h in the numerator as well. I don't do that because there's no need. Yep.
I was going to ask a question that has to do with like why we're only doing this in non-linear spaces, but that's the reason.
Right, because we have to have some way to define limit in order to take. I mean, is there a more general concept of derivative than normed linear spaces? Yeah. You can start looking. There's all kinds of abstractions of derivatives which may or may not even be connected to some notion of limit. You could do some sort of formal algebratization of it based on the algebraic properties of the derivative. But this to me is a natural extension of the derivative that you know and love from Calc 1. Maybe love is too strong a term. But here's a little lemma. If the limit as whatever, let's say v goes to a of f of v is equal to 0, that's interchangeable with the limit as v goes to a of the norm of f of v is equal to 0. Because we're looking at the limit being 0, I don't need to put the norm in the numerator. You could if you wanted to. All right. Okay, so there you go. That's your definition, and then so we can try to prove, basic various properties about this, right? All right. So let's do something. Let's pick some low-hanging fruit. Suppose T, T from one normed linear space to another is linear. What should the derivative of a linear transformation be? What's that? What's the best linear approximation to a linear transformation? Maybe we should hope there's a linear transformation. So here's how you actually do that, though. What we do is look at t of a plus h, right, minus t of a. Well, that's equal to what? That's equal to t of a plus t of h minus t of a. So as you can see, that just by linearity, right, by additivity. So that's just t of h. So then consider, we're going to say L of h is equal to what? So in order to prove that the linear transformation is differentiable at the moment, since we'll soon replace this with formulas that you guys will be happy about. But for the moment, we're working with the definition, all right? So to prove something is Frechet differentiable, I have to propose a linearization to the change. So my proposal, so what I'm calculating here is the change in t based at a, right? So here's the change in t, this guy. I calculated that the change in t is equal to t of h straight up. So I'm going to consider the linearization, the best approximation to the change in t, just to be th. T acting on a, t fed with a, words, t of h. So then the limit as h goes to 0 of what? Of t of a plus h minus t of a minus L of h, which is t of h, right? All divided by the norm of h is equal to what? Limit as h goes to 0 of what? Well, we just proved that, I mean, just right here I have just argued that, yeah, exactly, that this and this are the same. So we're just left with 0 over the norm of h. We're like, well, there's division by 0. Again, this is a limit. So we approach 0, but we don't get there, right? That's the construction of the limit as we take the deleted open set around the limit point. So in fact, Joe is right. This is exactly just equal to 0, which proves that, in fact, we can say this. The differential of a linear transformation at an arbitrary point A acting on h is just equal to t of h. And so if you like, you can just drop the t and say the differential of t is just t once more. So the differential of a linear transformation is the linear transformation again. This word differential I'm using for a linear transformation. We will soon talk about the Jacobian matrix, and that will be that will actually be the matrix of this differential. Okay? But one thing at a time. How about if we had a constant function? How about if f of x is just equal to a constant for all x in V? What's the derivative then? 0, right? Because you can plug it in, constant minus 0, same limit, 0 over 0. Again, you can sort through the definition. You get that the differential at any point A of the constant is just equal to 0. What other things are generically true for a, what if we have, next thing you might think about is, what if we have more than one function, right? What if we have several differentiable functions from V to W? Would their sum be differentiable? What do you think the derivative of the sum should be? Yeah, we would hope so. The sum of the derivatives, yeah. So let's suppose if f and g from V to W are differentiable at A, let's say x equals to A, and C is a real number, then CF plus G is differentiable at x equals to A. Moreover, there's a relation between the differentials. The differential at A of CF plus G, we should expect is C times the differential at A of F plus the differential at A of G. How do we prove that? Well, let me forgo the limits here and just point out to you, if we look at the change in CF plus G, what do we get? In other words, C times F of A plus H plus G of A plus H, right? Minus C times F of A minus G of A, right? Look at the change of this function, right? That's equal to what? That's equal to C times F of A plus H minus F of A plus G of A plus H minus G of A. But, of course, this is the change in F, right? And this is the change in G. And we know that those are approximated by the differential because we're assuming that these are differentiable. But just to be more explicit, I mean, that's why intuitively I expect this to work, but to be more explicit, let's call this thing H, right? Oh, bad choice. Let's see here. Call it 7.
Tell me where there's another number on the board that's not 0 or 1.
7 as a variable name.
Don't do it. Just do it.
Okay. So I can't do it. I can't do it. It's too much writing. But I will use this. All right. So. It's an S. It's not an 8. You people. Ampersand. Oh man. Fine. All right. I'm ghosting this argument. All right. So. Change in ghost. So excuse me. I'm gonna. Oh man, you guys are just. You've gotten me all off track. What have you guys done to me? Good gracious. All right.
You know it works.
Ah.
You're not going to use a 7 for the rest of the
Fine. Well, you've driven me to lambda. Lambda. Capital lambda. Capital lambda. Capital. You just want it to be 7. All right. So I'm going to say L of H is equal to what is it? It's going to be the differential at A of F times C of H plus the differential at A of G at H. So that's going to be my, this is my definition for L. And then you can check that if we look at lambda of A plus H minus lambda of A, minus L of H, right? What's that give us? So lambda. This is the change in lambda is already up here, right? So my point is the change in lambda. It has F terms. It has G terms. The F terms have a C multiplied outside. The G terms don't. You can group the F and the G terms together. Let me do that. So, the F terms, I get C, pull that C out. I get F of A plus H, F of A plus H minus F of A minus DAF of H plus G of A plus H minus G of A minus DA G of H. Right? So my point then is if you take the, I have, you guys, it's all your fault. It's all your fault. All right, so this divided by H, right, norm H, is this times 1 over the norm of h, right? And so here I have, well, I guess I can take the norm of the whole thing, right? Let me do that. So the norm upstairs is the norm in W. The norm downstairs is the norm in V. And so I have, this norm, and then outside I've got 1 over the norm of h, right? But then I have the triangle inequality, right? This is what? This is less than or equal to the norm c times the norm of f of a plus h minus f of a minus daf of h, all divided by the norm of h plus the norm of g of a plus h. Oh, I'm not sure this is actually what I want. Oh, it's fine. Yeah, I am trying to get as much stuff go to 0. Actually, I'm feeling better about it. I was starting to doubt myself because I was like, that having the thing on the one I'm writing right now going to 0 wouldn't suffice to prove what I want, but actually it does. So as h goes to 0, we have both of these things going to 0. Why? Because we assumed that f was differentiable and we assumed that g was differentiable. Yeah, well, it is, I suppose, but I mean, I'm assuming here that f and g are differentiable at a, which means that this goes to 0 and this goes to 0 separately as h goes to 0, right? Which goes to show you that the change in lambda minus the proposed linearization is going to 0 as h goes to 0, which then proves, in fact, that my definition for L was justified. And by the way, is this a linear transformation? Well, it's the sum of linear transformations, which is once more a linear transformation and scalar multiple. So there you have it. The derivative of a sum is the sum of the derivatives. Oh, excuse me, the differential of a sum is the sum of the differentials at the moment. I'm using differential as the word for the linear transformation, which is the best approximation to linearization. If we follow Edwards, he uses the word derivative for the matrix of this transformation. Okay? So he makes a technical distinction between differential and derivative, which I try to respect in my language. But I suppose this isn't terribly surprising. I mean, it would be kind of disturbing if you had this generalization of derivative and the sum of differentiable things wasn't, again, differentiable. That would be kind of annoying, right? But it's not the case. All right. One more abstract example, and then I will... and this example is not that abstract, actually. It's... a little bit more explicit. So my game plan today here, to give you another example, I'm going to state a theorem about continuous differentiability. And then I hope to use that theorem to prove something kind of interesting. And maybe I can reproduce this example I'm about to do in an entirely different way. Although I probably won't get to all that today, if I had to guess. Anyway, we don't have to hurry. We'll just take it one step at a time. All right, so another example. How about this? F of A is equal to A squared, where F is a mapping from n by n matrices to n by n matrices. So it's the square function for n by n matrices. All right. So what's the question is to calculate the differential at A of F. And we'll say, what is that acting on H? What's that equal to? Okay, so we don't have anything better to do right now except to just calculate directly the change in the function That's all we have at the moment is at our disposal is the definition. So we have to attack directly, calculate the change in the function, and see if you can come to grips with what that is. So what do I have to look at? I look at f of a plus h minus f of a, right? That's the change in the function at the point, right? So what is that? I just wrote it out like that to emphasize what's going on here. So when you get what? You get a squared, then plus what? Plus ah plus ha plus h squared minus a squared. What are you talking about? Oh, yeah. Complete accident, I'm sure. So those cancel, right?
You make everything else up on the spot. These are the things you plan out.
Everything else I make up on the spot, but this I plan out. Joe understands me. Let's see here. It's good. It's good, Joe.
Last semester I got points for making points.
Fortunately, my mic is sufficiently far away from that comment as to not pick it up. All right, now, so the question then is, just because you calculate the change, that doesn't mean whatever here is the differential. You have to kind of use, at the moment, some common sense. You look at it and you go, which piece of this is the linearization? Which piece is not? H squared is not linear in H. However, this right here is. If you replace H with H1 plus H2, you'll get the same thing with just H1 and with H2 added together. I mean, this is linear in H by properties of matrix multiplication. So what I'm going to say is I'm going to say that L of H is a ha. Or plus ha, to be more technically precise. And so then you can calculate the difference quotient, the Frechet, not difference quotient, I should say, the Frechet quotient. Calculate the Frechet quotient, which is the change in f, right? Minus L of h, and what does it work out to? Divided by the norm of h, right? So by what I just wrote up here, what cancels? Well, you see what canceled, right? So you're going to, I'll just write out, I mean, it's going to give me a plus ha, minus, well, a plus ha plus plus h squared, minus a plus ha. I regret this. Indeed. Now, so let's face the music here. So consider h squared over the norm of h, right? Now, I'm going to look at the norm of that. All right. So by properties of by the absolute homogeneity of the norm, I can pull the norm of h out front, right? And that's the norm of h quantity squared. By probably the hardest problem in the first homework, this is less than or equal to, I mean, this is HH, right? So by the Banach algebra inequality, that's 1 over the norm of h times the norm of h, right? So these cancel if h is not 0, right? And we get norm of h. So of course, 0 is less than or equal to the norm of h squared divided by norm of h, which is less than or equal to norm of h, right? That inequality follows from the Banach algebra estimate. That's the most evil problem in your first homework. And so by squeeze theorem, by the squeeze theorem, we have that the limit as h goes to 0 of the norm of h squared divided by the norm of h is equal to 0, which then by the lemma, which isn't hard to prove, implies the limit as h goes to 0 without the norm. Which just goes to show you that our aha moment was legitimate, right? Because that shows that the Frechet quotient tends to 0 as h goes to 0, and consequently the differential at a of f of h is equal to plus ha. I mean, so the stuff with the norm and the squeeze theorem is kind of a little bit disconcerting if you haven't seen it before, but a similar argument pretty much goes through. If you come up with any polynomial you like in matrices, what you can do is just plug in a plus h, take the difference of the polynomial you're given with the polynomial at a, and you just collect all the terms with just h in them. That will be the differential. That's what it boils down to. And everything else will have some higher power of h, which when you feed it to the Banach inequality will give you like at least one left over h in the numerator, which then tends to 0 by squeeze theorem argument. Any questions? Which jump? Oh, how did I get from there to here? So what I've shown is that this limits to 0. So since this goes to 0, as h goes to 0, that tells me this because I proposed that the linearization to this function is given by this. So this shows that it honestly is the best linear approximation because the Frechet quotient goes to 0, which again shows you that the change in f really is best approximated by plus ha in the linear sense. If you wanted the best quadratic approximation, throw in the h squared term.
Okay, so
But that wouldn't be a derivative.
d sub a f of h is equal to L of h, which is the best linear. So that with d sub a f is.
I mean, this is just a transitory definition I use because I don't want to write d sub af everywhere. Because at some point or another, it'll look kind of circular if I do that. It'll be like, well, you said the derivative was that here, so why are you proving it?
Okay.
That's part of the reason that I use an L here,
So
to free your mind from the idea that it's already known.
So the derivative here is saying the result of the derivative equals the best linear approximation, which just happens to be
Right. Yep. All right. Now, grab my notes. So I'm going to change gears here a little bit. Not too much, really, but we'll talk about the generalization of partial derivatives, right? So, do you guys remember how we defined partial derivatives? Yeah, you guys remember this. I can erase it all. How do we define a part? I mean, what does this have to do with partial derivatives? Yeah, remember partial derivatives were directional derivatives. Where, in what directions?
direction
Right. Well, true in retrospect, but in the direction of x, y, and z, right?
Yeah.
But yeah, I'd like to define partial derivative in the direction of a basis vector. That's not currently in my notes, but it's really not hard to do that. So let me just lay it down on you. So first of all, what's a directional derivative? Start there. What's a directional derivative? So conceptually, what it is, I mean, in our context, we're still thinking about a function from, some perhaps open subset of a normed linear space V to W. But basically what the directional derivative is it has to do with studying how that function behaves along some line. So, well, let me just get to it. I'm going to use a big D for the directional derivative, big D F at the point A in the direction V. I know it's an obnoxious notation, but that way we'll have a clear separation of it in our mind from the differential notation, which is something different. So the directional derivative of f at A is simply defined to be the limit as h goes to 0 of f of A plus hv minus f of A divided by h. We dropped this assumption that V has to be a unit vector when we study advanced calculus. In Calculus 3, as to say things that are easily communicatable to a large mass audience, we assume unit vectors so we can say things about the meaning of the magnitude of the directional derivative without qualification. Right? The directional derivative, when you use a unit vector, describes the actual honest-to-goodness rate of change of the function in the direction V at the point A. If I don't force V to be a unit vector, well, if you have different length V, you get different rates of change, right? So if you want to have a uniform judge of the rate of change of the function f, you need to fix the length of V. But we won't do that because it doesn't help our larger purposes here. Our larger purpose is to connect this directional derivative with the Frechet derivative that I just showed you at the start of class. All right? Now, what is this really? Well, another way to look at this is that this is the derivative with respect to time of f of A plus TV such that, well, let me write it this way, parentheses, at the end of everything, put t equals to 0. Although that kind of begs the question, how do you differentiate with respect to time f of A plus TV? I mean, f of A plus TV is in the space W, which is an abstract vector space for us at the moment, all right? So let me give you a definition for this derivative. Here what we mean is that if f is equal to, let's say, the sum j equals 1 to m of f sub j w sub j, where f sub j are mappings, from, for the moment from R to R. So these are actually just real functions, all right? Then if we talk about df dt, what we mean by that is just differentiate component-wise. So this is just like the definition you saw in Calculus 3 for like differentiating a space curve. You just differentiate the x component, you differentiate the y component, you differentiate the z component one at a time, you just do it component-wise. I'm just saying do the same for an abstract vector space. You do it one component at a time. So that is what I mean when I write this derivative with respect to time of f of A plus TV up there, okay? We good?